Okay, so I've got another differential equation on the board. Surprise, surprise, it corresponds to an undamped yet forced harmonic oscillator. Okay, undamped because there's no y prime term, forced because this is not homogeneous. That's not zero, so this is the forcing function that we're applying. Okay, so I know my solution is going to be a solution to the associated homogeneous plus a particular solution. To find our y sub h, the associated homogeneous equation is y double prime plus 9y equals 0. Characteristic equation is s squared plus 9 equals 0. So s is plus or minus 3i. So a complex solution would be e to the 3it. E to the negative 3it is another. But one complex solution gives me two real solutions, so I need only one, because I know that this is cosine of 3t plus I times sine of 3t. That's the real part, that's the imaginary part, and y sub h is just an arbitrary combination of them. So we'll have a copies of cosine 3t plus b copies of sine 3t plus our particular solution. Okay, excellent. So now, you might have noticed that our solution to the associated homogeneous, so the natural response, has an angular frequency of 3. That's the same as our forcing function. Now, we've said that when they're close, we get beating. But all the work that we did when they were close is completely irrelevant here, because when they were close, we were always getting a fraction where it was 1 over that angular frequency squared minus that angular frequency squared. When they're the same, that's going to put a 0 in the denominator. We can't have that. So we're going to have to adjust. Now, I'm still going to complexify. So I'm just recycling the name y tilde. A moment ago, it was a particular function. Now it's an unknown complex solution to this complexified equation, e to the 3it on this side. Okay. Now notice, because we've got a sign here, that's the imaginary part of this. Okay. So ordinarily, I would guess yp tilde would be a multiple of this. But I know it's not, because any multiple of this is a solution to the associated homogeneous equation. So I need to modify my guess, and I'm going to do it in the usual way. I'm going to just multiply it by t. So I'm going to guess that I have some copies of t, e to the 3it, and I want to solve for the a that will make this work. If I can find such an a, my real valued particular solution will just be the imaginary part of my complex valued particular solution. All right, so let's see. If I take yp tilde prime, looks like we're using product rule. I'm just going to view that first factor as at. So we're going to get an a, e to the 3it, plus at times here the derivative is 3i, e to the 3it. Yp tilde double prime. Here I'm going to get a 3i, a to the 3, a e to the 3it, plus, again, product rule, and I'm just going to bump all those constants with that first factor. So here the derivative of that first factor is 3ia times e to the 3it plus 3iat times 3i times e to the 3it. Beauteous. So these two guys are like terms. In fact, they're the same, so I'm just getting two copies of them. So I've got 6i, a, e to the 3it. Here, the 3 and the 3 are going to give me a 9. The I and the I give me a minus 1. So I'm getting minus 9at e to the 3it. All right, if this is going to work, I've got to be able to plug into this equation and have it be true. So I need yp tilde double prime plus 9yp tilde to equal e to the 3it. So the second derivative we just said is this, 6ia e to the 3it minus 9at e to the 3it plus 9 copies of my particular solution, so that's going to be 9at e to the 3it, and all of that has to equal e to the 3it. And isn't that lovely? The t e to the 3it's just drop out, which is great. So that leaves me with 6ia e to the 3it has to equal 1 copy of e to the 3it. Well, that'll only work if 6ia equals 1. So a is 1 over 6i. I'm going to multiply by 1 in the form of negative I over negative I. I over I would work. Negative 6i over negative 6i would work. Negative 6i is the complex conjugate of that. Okay, I'm viewing this as 1/6 the reciprocal of I. And I'm using the complex conjugate of I, which is just you change the sign of the imaginary part. The reason I like to do that rather than just I is now I get negative I on bottom. Negative I times I is positive 1 times 6. So I get a positive number on bottom. I just kind of like that. Okay, so now I know that yp tilde is negative I over 6 t e to the 3it. So that is negative I over 6t cosine 3t plus I sine 3t. Now, since I'm multiplying by an imaginary number here, that's going to change which parts are real and which parts are imaginary. So notice I'm going to get negative I over 6t cosine of 3t plus 1 over 6 t, 1 over 6t sine of 3t. I times negative I gives me positive 1 over the 6. Okay. Now, we said we wanted the imaginary part, so my y sub p is this part right here without the I. So negative 1/6 t cosine of 3t. All right, so that is my general solution. Now, what does that mean? Well, here's my natural response. That's just oscillating with fixed amplitude. This is oscillating with an amplitude that's growing, because this is going to be alternating between the lines y equals 1/6 t and y equals negative 1/6 t. So I'm going to combine a fixed amplitude with something that's growing. I'm ultimately getting something that's growing. So if I just graph lines of slope 1/6 and negative 1/6. Now, exactly what lines I get, exactly what the y-intercept of those lines is going to vary depending on the initial condition. But the slopes of the lines will be plus and minus 1/6. Okay. So, I can have something, let's see, that goes up 1 over 6, so not too. If I'm just going to draw some lines of slope plus and minus 1/6, and I'm going to have then curves that are oscillating like so that the amplitude is growing. And when that happens, we call that resonance. So, when you have the opera singer who sings and breaks the glass, that is resonance. When you have a bridge that collapses because of strong winds, or even because of just people walking across it, interesting examples in the textbook, that may be due to resonance. Okay, so if you're designing a bridge does behave, at least a suspension bridge does behave like a harmonic oscillator as it responds to the forces that are acting on it, and you need to make sure that you're avoiding resonance so that your bridge does not collapse. Now, we're only covering the first 3 sections of Chapter 4 in this class. Section 4.5, though, does talk about the Tacoma Narrows Bridge. And it's an interesting read, so I'd encourage you to read it if you're interested, in particularly if you're an engineer who's ever planning to build a bridge or design a bridge. Okay. Bridges falling down is a bad example of resonance. That's something we like to avoid. Something that can be good is if you have a radio signal and it's really faint, but they're playing your favorite song. So you want to amplify the radio signal so that you get to hear it a little bit better. That can be something where we have resonance that we're trying to achieve. Okay. All right. So if I give you something with resonance, I would ask you to basically find the general solution. And again, just draw a representative solution curve. What will always be the same is the slopes of these lines. The y-intercepts will vary depending on what the initial conditions are. And also, where you start in your oscillations will vary depending on what the initial conditions are. But this shows the overall pattern. So for the purposes of qualitative analysis, it does a pretty good job. And then if I had a particular initial condition in mind, then I could always fine-tune things if I needed to.